Okay, so today we're going to talk about some different ideas surrounding forces, some different forces that you may have heard of, and some different topics that are all related back to forces. So the first topic we're going to talk about is gravity. Okay, we use gravity all the time when we're talking about how things fall to Earth, how things change their speed as they fall. But gravity in itself is attractive force between any two objects. So we always normally use gravity when we're talking about things falling, but essentially it's just if you have two different objects, and given the right circumstance, they're going to be attracted towards one another. So, for example, there's a gravitational pull that pulls the Earth, even though it's in rotation, wants to go closer to the Sun. Things that are moving throughout outer space are going to want to go towards certain things depending on the gravitational pull. Black holes have a very strong gravitational pull, and things get sucked into that. And that's just because there's a force that's greater for a black hole than other things. We won't get into the specifics of that, but that's what it means. So gravity depends on the masses of the objects and the distance between the objects. So the further you away are from something, the less the gravitational force will affect you. A mass will make something greater. So move on to the next thing. So the acceleration due to gravity. So as you're falling, the way you will change speed, as long as you don't have, if you're neglecting air resistance, is this right here, 9.8 meters per second. Okay, so we're not talking about the actual force of gravity, but we're saying that as gravity pushes you down or pulls you down to Earth, you will change your speed constantly with 9.8 meters per second squared. Okay, but the actual force of gravity, the gravitational force that pulls you down, is a combination of the mass of whatever object it is, you or whatever object, times the acceleration of gravity. Okay, so we can say this is little g right up here. So let's review real fast about what mass is. So again, this is from the very beginning of the semester, the amount of matter in an object. Okay, so you can find your mass by standing on a scale, an actual scale. So a gravitational force exerted on an object is the object's weight. So that force exerted on an object, and what we do is we have to multiply the mass of the object times the acceleration due to gravity, or how fast you would change your speed if you fell. And that would give you your weight. So if we're asking to find weight, really the only difference is you would use this as a W, which you can also say is a force. Okay, so the weight is equal to the mass times gravity. Okay, so weight can change as the gravitational force on objects change. So for example, your mass on Earth is going to be the same as your mass on the moon. It's never going to change because your mass is your mass. But as you go to the moon, for example, your weight will be different because the acceleration due to gravity on the moon is way less. Okay, if you went to Jupiter, the acceleration due to gravity on Jupiter is way more than Earth, and so your weight would be greater. A couple of different things when we're talking about gravity in different situations is one of them is free fall. Okay, so it's the force of gravity still acts on you, and then weightlessness, you feel weightless because you no longer exert a force down. That happens whenever air resistance and gravity and then air resistance, so air, have a net force of 0. You no longer feel as if you have any weight, you're just floating. Okay. Another way we can talk about forces is if the motion is projectile through the air, and we're going to talk about gravity and how that relates to it. So a projectile in general is anything that is thrown or shot through the air, and that I think we can understand. That's a pretty common word. But gravity is the thing that causes projectiles to flow on a curved path. So if we shot or let's say we tried to shoot a basketball, okay, the ball will go like this and hopefully land in the hoop. Okay, the reason why you don't just see the ball go up in the air once you throw in that direction is because gravity is pushing down on the ball. Okay, so there's always two motions with this. There's the horizontal, so it is the motion going in this direction, and then there's the vertical, which is how gravity is affecting it. So it's going to make that combination into some sort of curve. Okay, that combination makes it some sort of angular curve like that. The two different motions are independent of one another. So the horizontal and the vertical, they're two different things. The horizontal motion can be constant while vertical motion is changing due to gravity. And that makes sense because if you throw something in this direction, it's just going to keep going in that direction. Okay? But however, the vertical motion may change. It may initially start going up, but then once gravity affects it, it's going to start changing. So this motion changes, the vertical changes, but the horizontal stays the same. However, with distance, objects travel the same vertical distance in the same time, even though one travels more horizontal distance. Okay. Continuing on, there's another type of force called centripetal force. Okay, and this is the acceleration towards the center of a curved or circular path, and they call this centripetal acceleration. Okay, so the net force exerted towards the center of a curved path is the centripetal force. And gravity, for example, can be a centripetal force, Earth's revolution around the sun. So as Earth moves, and we'll say this is the sun, Earth moves, okay, it's constantly being pulling towards the sun, but since it's locked in this orbit, it creates this circular or centripetal force. Okay. Another example is that if you're in a car and you're driving on a curve, okay, you know that as you turn, you're being pulled in one direction. You guys have seen that if you've ever been driving or in a car and you've got something in your hands. If you're going in this direction, it's going to try to go that way, right? And that's because the centripetal force is pulling you out as long as also in, but the path of inertia technically is going in that direction. Okay, and on the next slide, it actually talks about this. So when you drive your car around a curve in the road, centripetal force acts on your car to keep it moving in a curved path. It actually pulls you in on that path. Okay, so like right here, as you're traveling on this curve, it pulls you towards the inner part of that centripetal curve right there. So this force is actually something we do with friction. Okay, it's another frictional force. It keeps your surface between you and the road to keep you heading in the right direction. But if it's been raining, how is your frictional force affected? Is it going to be as good? Probably not, right? It can't keep you on the road as good. So that's what happens sometimes. Our tires meet the road and it's fine. But whenever something interacts with the surface of the road to our tires, let's say water, that force may interact and it may not be as good. Okay, so if that force is not as good as it used to be, all of a sudden you'll see a car out in the ditch, you'll see it in a wreck, you'll see something happen. So traction will not be as good if the frictional force or the centripetal force is not as good when you're driving on a curve. So that's why it's always important to slow down when you go through curves, because if something like water was to hit your tires and mess up the frictional force, you could end out somewhere other than the road. Okay, so we've talked about Newton's first law, which was the law of inertia. The second law was talking about the relationship between mass times acceleration, and that equals to a force. And the third law describes this, the action and reaction. So when one object exerts a force on another object, the second object exerts a force on the first that is equal in strength and opposite in direction. Take this person, for example. She's pushing on this wall. Okay, the wall, because there's a force pushing on it, is pushing back at the same amount. So to every action, there is an equal and opposite reaction. This is probably the most important phrase when we're talking about Newton's third law. So if I was to put this in a quiz or a test and I ask you which law does that represent, that would be Newton's third law. Okay, so action and reaction forces. So action and reaction forces are equal. How does this happen? For instance, if you push down on the water and the water pushes back, why are you propelled through the water if you're swimming, for instance? Well, action and reaction forces, they can act on different objects, and even though they're not equal, even though they are equal, they are not balanced. So you may still be able to do stuff, but you're actually using other factors besides just those two instances. When you push on the water and the water pushes back, there's other things that are happening that they'll equal out those reaction and action and reaction forces. And the last thing is we're talking about is an example of rocket propulsion. You guys have seen rockets. You've seen them in movies. You may have seen something on the news about them. And as a rocket burns fuel, it produces hot gases. And the rocket exerts a force on the gases, and it causes them to escape out the back. The gases in turn exert a force on the rocket and cause it to lift off. So pretty much if you've got a rocket, this is going to be our rocket, it exerts a force down. But by doing that, it creates a force that's going to be pushing back up. And that force is going to be so great that as it pushes, it's almost making it do like this. It's making it go up in the upwards direction. Okay? So I hope that's clear for everybody. Make sure you got those words written down. Thank you.